Hello everyone, my name is Tychonas Michailidis and I will be presenting this paper, Implementing Remote Audio as Diagnostics Tool for Maritime Autonomous Surface Ships, on behalf of my colleagues Christopher Barlow, Gordon Meadow and Eshan Rajabally. The paper presents how we use remote servers to simulate and test the hypothesis of the project named Imagine, which stands for Innovation in Maritime Engineering, Diagnostics and Feedback. The project was a collaboration between Warsash Maritime Academy, which is part of Solent University, and Rolls-Royce, and ran for just over 2 years between 2016 and 2018. The aim of the project was to have a better understanding on how engineers act while on board and how they identify and diagnose issues and failures while on board. And also how we could transfer that and communicate those feedback mechanisms so that engineers would be able to have the same information to do their jobs effectively from a remote location. In short, this project was to identify what is needed to remove engineers offshore and to be able to do their job. While there are a few options to choose from, and we examine how how virtual reality was used and how we could make possible that so that engineers will experience the engine room from a remote location. Since there was an industry patent, we believe that any made-up scenario with made-up data, including audio and graphics, would not have been realistic and would have resulted in a rather unconvincing outcome and not reflect the industry. For that reason, we approached a ferry company named Red Funnel, which operates from Southampton to Isle of Wight in the UK, and they gave us access to one of their vessels and the engine room to basically simulate the engine room in a VR simulator and collect the data that we needed. The picture on the bottom left shows the engine room, and the top right is an early stage of the simulated version. Here again you can see on the top left the compressor and then the simulated version, and also the arrows identify where each item is in the engine room, and how you can see how the early version become the final version on the right hand side. And also the far right picture shows the viewer's point of view, so how the engineer would look at the engine room when they put the VR headset. To understand better how a maritime engineer works, there are a few universal characteristics or general rules that we can go through. When there is an alarm, an engineer assesses the criticality of the alarm and acts accordingly. The systems do not monitor every single component in the engine room. Alarm systems tend to provide only the basic information to the engineer, such as tank level low, and depending on the alarm, an engineer enters the engine room to investigate further the cause of the alarm and gain more information about the system in question. The loudness in the engine room is more than 100 decibel, therefore ear defenders are required. Engineer inspects the engine room at the start and finish of their shift, what is known as rounds, to identify and prevent any major failure. For example, during rounds, an engineer might spot a leak, which at the time might be insignificant to trigger an alarm, but it will develop in the future and it will cause more damage. This is a typical engine room alarm system. As you can see, the information of the alarm is basic, such as temperature high or low, without necessarily providing the root cause of that failure or any further details. And again, this is an engineer that is checking the equipment using his hands. So he's checking if there's heat and if there's vibration through the pipes, so that in order to confirm that the data of the alarm are correct. We set up a server in order to enable the use of a real data and audio as if they are streamed from a real uncrewed vessel, into the control center where the engineer will be experiencing them remotely. All systems in the engine room were recorded while in operation, and the server was controlled through a web interface that enabled us to introduce any failure that we wanted for the user testing. The user is able to experience three sets of data. That is current data, so that's what's the current data at this given time. The baseline, which is what's considered to be normal values when in working condition for that particular component, and the history, which refers to the values of the component up to 10 hours before. This enables the user to have a good overview when signs of failure might occur, or how they developed within the past 10 hours, and how might be associated with other changes of other machinery within the engine room. The main focus of this project was how audio and sound could be used as a diagnostic tool. However, in order to test if an engineer could identify a failure through sound, we had to record the sound of a failure of all the components of all possible failures. This was an impossible task, as in theory we had to wait when a component in the engine room would break in order to record it. In order to go through these, we used the original recording from the original audio from the recording, and we added sounds of a particular type of failure based on that component. This includes sounds from a failure of cavitation, bearing, rotor, jamming, misfire, and knocking. In addition, each component with the associated failure was represented in 4 different levels in order to simulate the severity of the failure. So we had very low, low, medium, and high. In the picture you can see the frequency analysis between the clean recording of the pump and the process audio of cavitating pump. We also provide the option to isolate audio from the selected component from other sounds in the engine room to be able to focus on that particular component, something that is not possible in the real engine room. For the user testing, we ran a usability test with 7 maritime engineers of an average 27 years of experience. They were asked to assess whether or not they felt there was a potential system failure and what might have caused that failure and possible further actions, or if the system was operating normally. Each user ran through 4 different scenarios, 2 of which had faults and 2 of them were running as normal. The audio was specialized using binaural encoder for built-in HTC Vive Pro. Thus, we were able to experience and feel the audio in a similar manner as in the actual room. 4 out of 7 engineers were able to identify if something was wrong and what might have caused the failure, but stated that they would need more time to investigate further in order to identify the exact type. The remaining 3 participants diagnosed the correct failure. The overall response focused around the immersive features, and sound was discussed in 53.9% of quoted phrases. While we acknowledge that the focus of this project was around the implementation of audio, and is interested to see such results, we assume that the high percentage of sound was due to the way which was experienced and presented to the engineers, which is something that's impossible to do in the actual engine room. For example, the ability to isolate sound of the machinery from background noises. The following is a short excerpt of a video recorded through the headset of a user where he tries to identify the failure.
That's right, yes.
Thank you for listening.